Welcome to your channel, Thermal Engineering Concept and Principle. This is Professor Ali Tarrad. This is a special issue to celebrate the first anniversary of your channel, our channel, with your participation and contribution. We were able to publish quite good number of episodes, more than 100 videos in the field of energy management, energy sources, renewable energy, including geothermal energy, heat transfer, and its application. Thank you for your support, and I hope that you will continue in what we have started 1 year ago. In this special issue, I will cover some of the videos which have been published in our channel, and thank you for everything. Without your support, I could not continue in participating to the community by providing the information, useful information in the energy field and heat transfer. And at the same time, I wish that we can continue at the same motivation parts which we have started. Thank you, and let us go through some stages of our project, which is free of charge, just to provide the knowledge and information for the people who needs it. Let us go through these videos. Thank you. Welcome to my channel, Thermal Engineering. I am Ali Tarrad, and after 35 years of experience in engineering, I still think it is fascinating. This is my first attempt on this channel to give back to the scientific community. So I appreciate your comments, feedback, and what subjects that you would like me to cover in the future. Let us start with heat transfer modes. Here we have some of the contents which has been published in this channel. We passed through heat transfer modes, their applications, industrial applications in heat exchangers, water chillers, cooling towers, and many other industrial and technological parts in this field of engineering, where energy is the principal factor in these equipment. We also passed through thermodynamics of Rankine cycle, the main components of this cycle, which is used in electricity production in power plants. We applied first law of thermodynamics and waste energy recovery, how can we use it to produce electricity and improve the efficiency of plants. We also focused on the geothermal energy in power plants and heat pumps. And finally, we arrived to the thermal design of geothermal borehole. Finally, we may find a mathematical treatment for these modes in this part where the conduction is usually defined as Q equal minus K A dt by dx. K is the thermal conductivity of the material. A is the surface area, which is usually considered as the perpendicular surface area to heat transfer, and dt by dx represents the temperature gradient. For convection, we have the heat transfer rate is equal to H times A delta T sub W. We have H here, the heat transfer coefficient of the fluid. A is the same, the surface area of the contact heat transfer area between the fluid and the solid. And delta TW represent the temperature difference between the wall of the object and the moving or still fluid. Finally, we have the radiation, which is defined in a general form, sigma absolute A1 F sub 1, 2, and then the temperatures are powered to 4. We have sigma, the Stefan-Boltzmann constant, which is fixed value, and F sub 1, 2 represent the shape factor, which is usually less or equal to 1. It is defined as the fraction of energy leaving surface 1 that reaches surface 2. The emissivity factor falls within the range of epsilon, which is less or equal to 1. We should note that radiation does not require a material medium for energy transfer. Is unlike the conduction and convection modes. It can be transferred through vacuum, through gas, or liquid. And this is the final part of this seminar, and I hope that you will enjoy its content. The fluid flow arrangement in the heat exchanger, and as we are talking about shell and tube heat exchanger, is the same for other types of heat exchangers. So there are two main types of fluid arrangement in the heat exchanger. The first one is called the counterflow pattern, and the second one is called the parallel flow pattern. In the first type, the fluids on the shell side and tube side enter the heat exchanger from opposite ends of the heat exchanger. Therefore, as they are passing through the heat exchanger, the flow is counterflow.
And at the same time, when we talk about the other type, the fluids enter from the same end or the tube on shell sides, and they are leaving at the other end at the same direction. Therefore, these fluids, as they are passing through the heat exchanger, they are following a parallel path. So if we talk about the counter flow heat exchanger, if we have a look at the blue line, which represents the cold fluid, it enters at T sub Ci and leaves at T sub C naught. And when we have a look at the exit temperature, it will be there is a possibility to be higher than the exit temperature of the hot fluid. On the contrary, there is no possibility if we have a look on the right hand side um, graph, the cold fluid as it enters at T sub Ci, then it leaves at T sub C naught, which there is no possibility to be higher than the exit temperature. And in general, all the heat exchangers are preferred to have a counterflow. And in the counterflow, there is a uniform temperature distribution and they provide a good temperature difference between both fluids. So it is more efficient than the parallel flow pattern.
In the energy sector, and especially for waste energy recovery and power plants for electricity production, the Rankine cycle is usually used even in the geothermal systems where we can produce electricity in power plants. And this channel published quite good number and information about the Rankine cycle and its utilization. I have selected one of the slides from our lectures, which describes the TS diagram of the Rankine cycle. In this part of the episode, we will talk about the TS diagram. And as long as we are talking about Rankine cycle, which is used in power plants, usually it is represented on diagram or graph as shown in this illustration. Usually fluids have a curve. Uh, for example, for the steam is represented by the blue curve. To the left is liquid. To the left of this curve, liquid, uh, it is called subcooled liquid, in fact, because its temperature below the saturation temperature of the liquid at the operating pressure. And on the blue line, when we reach the blue line, then we will have a saturated liquid. The dome of the curve, there is a point which occupies the highest values. It is called the critical point, where we have a critical temperature and a critical pressure. To the right-hand side of the curve, where we reach the blue line to the right-hand side, it is called saturated vapor. And to the right of this line or part of curve, we will be in a zone called dry steam. And here we have the steam is superheated steam. And superheating, it means that the temperature of the steam is higher than the saturation value at the operating pressure. To represent the cycle which we have shown in the previous part of this episode, let us assume that the inlet to the pump is subcooled at a temperature T1. And usually there is something called the isentropic efficiency related to the pump, and the temperature will approach T sub 2 isentropic, where we have S is constant, the entropy is constant. In the actual term, the operation through the pump will follow the curve or the line, the black dotted line to reach a temperature T2, and that will be at a constant pressure where the inlet at the boiler is T2 and it passes constant pressure, extracting energy, heated up until it approaches the saturated value of the liquid, where here we can get liquid and vapor phases as continuing to heat up the liquid. Then a part of the liquid will be evaporated at P constant, and especially for pure fluids, then we have T constant as well, and approaches a saturated value, which is saturated vapor. And after that, in the boiler, usually it is superheated to a temperature which is represented by T sub 3. And in boilers, usually the temperature is so high, maybe 560 Celsius or more, and the pressure is high as well. So at T3, then this is the condition where it enters the turbine. And again, in the turbine, if we assume the constant entropy or isentropic process, then the expansion will follow the blue line, and the temperature, the pressure is reduced to a low value. But in a practical, it will follow the curve, the black dotted line with a value of dryness fraction greater than 90%. And that means we have at the exit of the turbine, there is a part of it is liquid and the rest is vapor. Then it enters the condenser at a condition of T sub 4. Here the condensation process is assumed isothermal and P constant. Then the liquid which is obtained as a result of extracting, rejecting energy to the cooling water, for example, which is supplied or provided from a lake, a river, or even a cooling tower. Then it will reach the saturated value, saturated liquid, where usually in the practical power plants, this temperature is reduced to T sub 1 as a subcooled liquid before entering the pump, and that to improve the thermal efficiency of the plant. This is how usually the Rankine cycle is presented on TS diagram. Of course, this is for the simple cycle, but again, it can be used as a guide for the complex Rankine cycle, because usually we have other uh, helpful or assisted components such as heaters were are used to preheat water before entering the boiler and can be added to this graph.
In this system, we have the heating mode where Earth works as an energy source to the fluid which passes through the borehole in the blue direction, which extracts energy from the ground and then return back to a heat exchanger, which is a part of the heating pump. Then this fluid will give uh, energy to another circulated fluid, which we have explained in the previous slide, and then that will provide energy to space. In that way, we have extracted energy from Earth and transferred to for example, domestic use in this example, then heat can be transferred from ground to the utility. In this case, we have the utility as heating for um, house or maybe in a restaurant or other applications. So this is the heating mode, how the heating mode operates.